Hello and welcome everybody once again. Today we are going to discuss one of the most important and practical aspects of computer graphics, that is how to develop your own application programs, or provided an API or an application programmer's interface, how to draw pictures and simulate pictures on the screen. And as mentioned in the introduction of the lecture, we are going to follow the industrial standard, which is OpenGL or Open Graphics Library. So, today the discussion will be on the graphics programming using OpenGL. Okay, that is where we start today. The first discussion is why OpenGL. Well, there are a variety of reasons or various reasons why OpenGL has become a standard, and there has been a gradual transition from the old standards. We talked of graphical standards in the introduction part of this course, and we started with core graphics, moved on to sRGB, FIGS, SFIGS, and finally, the world community almost has accepted OpenGL as the current standard. Of course, things could change in the future, but we will follow the standard as of date today, which is OpenGL, and it is available on various platforms. So, coming back to why OpenGL, the first reason is device independence, which you can see here. Okay, that is, you should be able to run OpenGL independent of the device you are using. That means, today if you run your OpenGL program on a certain manufacturer's keyboard, mouse and monitor, tomorrow if you move on to another system which has almost entirely different platform, the mouse has changed to a different manufacturer, different type, different make, the keyboard, the mouse, or even the processor or the operating system in certain cases. Okay. Then you should be able to run your program with almost no change. Of course, when you change from one operating system to another, it could be a case where you have to make some operating system related changes or compiler related changes maybe, but in terms of graphical calls, graphical functions, which we have seen through all the theories which we have analyzed so far, starting from transformations to clipping to rendering, shading, all those operations which we have studied so far, projection geometry, let us say, the command syntax and the command name in fact does not vary at all. So, that is the advantage which we have by sticking to a particular standard, because if you do not follow a particular standard, there are lots of difficulties which one can face. The number one is nobody will be the number one point is nobody will be able to understand your program, because you may make a program, but it may be necessary for somebody else at a later point of time to alter the program, modify the program, enhance the program's capacity, okay, and provided add-on values. So, if you do not follow any standard and write your own graphic routines, and that is followed by a group of people in a computer graphics team, and you cannot be you will not be able to share it with somebody else. So, software maintenance, reuse, all those factors have a big role to play, why we need corresponding graphic standards, and device independence is very much welcome in this particular scenario. Now, the question comes is how to use OpenGL. I did mention this in the introduction lecture, that almost any operating system, you name it, which exists in the world, starting from all varieties of Windows environment to Linux to IRIX to Sun Solaris, all different, or even Mac OS, you should be able to download OpenGL drivers, DLLs, header files on your system, which goes on along not only with your operating system, but also goes along with your driver cards, which are sitting on your system, and once that is configured properly, or what I will say as OpenGL ready. If the system is OpenGL ready, you should be able to borrow or pick up any OpenGL program, open source program available, or borrow it from your corresponding client or another group member, and then straight away use it almost with no change or very little change. Very little change you might have to make if you are moving from one system to another. So, that is the device independence part of OpenGL, which is talked about here as the first point in the slide, which you have seen here. The number 2, yes, it is almost the same which we were talking about, platform independence. Okay. We are talking of various types of platforms starting from SGI, RX systems and Linux systems or Windows. Now, the platform independence is different from a device independence. Let us see the difference. What is this difference? Well, in the same platform, it is possible that you could change a device. You could change your device, tomorrow the keyboard does not work, tomorrow the mouse does not work, or you are not satisfied with the monitor or the monitor's resolution. So, what do? You pick up another monitor in place of that in any of these cases. Okay. So, that could happen with any system. That is the, and still you want your OpenGL programs to work on that. So, that is the device independence part or the characteristics which as a feature which you want in the system. When you talk of platform independence, we are talking about the entire program being shunted out from one system to another, portability when you talk about. Okay. So, you should be able to take your programs from Linux to Windows, vice versa, or take it to any other SGI, RX based systems, okay, and it should work. So, that is platform independence. Device independence talks about interoperability from one device to another in terms of device components of a system, whereas platform independence talks about interoperability over various platforms. You want the seamlessly the program to just hop from one machine to another and work straight away if possible. So, these are the two factors which dictate why you want OpenGL. Well, we talk of these abstractions later on in OpenGL, where we talk of a GL, GLU and a GLUT or GLUT as it is called. GL stands for graphical library, that is it's open, that is what OpenGL stands for, Open Graphics Library. GLU stands for Open Graphics Library Utility. And what is GLUT then? GLUT, Open, it is Graphics Library Utility Toolkit. Okay. So, these are different level of abstraction, one sits on top of the other, certain high level features are available in GLUT which are not available in GLU. GLU has certain features not available in GL, we will see that later on. Okay. I will bring in those three stages one by one at later point of discussion, where we are talking about base level constructs available in GL and a few more advanced features in GLU, and GLUT is something like almost as a toolkit available to you, very high level interface with the Windows GUI and things like that. Okay. So, this is what we will talk about abstractions later on when it comes to OpenGL. Well, it is an open source, that means you should be able to obtain vendor specific information in terms of not only the DLL device drivers, header files for your particular monitor and systems devices which you are using in a platform, but you can have open source codes available. Okay. Open source codes available which you can download and use, and you can design your own DLLs if necessary for a certain device, and it is free to use. Although it is picked up as an industrial standard currently, and most universities also follow the current OpenGL syntax, but it is open source like Linux and it is freely available. So, that is what is OpenGL for you, it is open source. And then we are talking about OpenGL as a hardware independent software interface. It is a hardware independent software interface. Well, OpenGL is a software interface for a graphics hardware. It is a software interface for any graphics hardware, that is the target. Of course, there could be some few specific hardware components where OpenGL may not work. What I mean by do not work is the following, that there may not be the corresponding dynamic link libraries or the DLLs or the header files available for that particular hardware component right now, which are not ready to be interfaced and used. Otherwise, it is a graphic interface for it is a software interface for any graphical hardware, that is the typical one. Okay. And OpenGL's main purpose, why do you use OpenGL? Its main purpose is to render 2-dimensional or 3-dimensional objects. Okay. That is the main purpose why OpenGL is used. We will come to that point in a little bit later on, what are the different features in OpenGL, but as we go along this point, we will finish these points about why OpenGL and discuss in detail about why do you need to use OpenGL. So, it is a hardware independent software interface to be used, and it also supports the client server protocol. That means, you can run it over a network. When you talk of client server protocol, either using X Windows for Linux, or you are talking of an environment over the Windows NT type of network client server interface, the OpenGL is expected to work. okay, supports the client servers protocol, at least in terms of X Windows protocol client servers model. The OpenGL does not have a problem. We assume here that when you have a client and a server, of course, in a traditional concept, when the client sends request to do some service and the server service is that, we are talking of an OpenGL servers, which server sitting, let us say, which can handle all the graphics commands, all the graphics manipulations requested by the client. And that client may not be the same machine, that process may not be on the same machine. It could be a remote machine sitting on a network. It could be a remote machine sitting on a network which is requesting the service, and the OpenGL server serves that. So, okay, so that sort of a support of client server protocol is also supported or taken care of in OpenGL. Okay, so support of the client server protocol is one important point, and the other point is we have the other application programmers interface like the Open Inventor, also by SGI, which is an object oriented toolkit available. And of course, you can have DirectX of Microsoft and Java 3D of Sun Microsystems are alternatives of OpenGL, which make your life easy if required. So, these are all the toolkits and software interfaces available for OpenGL to work along with this. Okay, you do not have to worry too much about trying to interface DirectX or Java 3D along with the OpenGL, they mesh quite easily. So, now the question comes, with all these traditional work, what are the features of OpenGL? We will move towards next, but I hope for the time being the idea of why one uses OpenGL right now is very, very clear. Okay, there has been standards earlier, like we talked about the old core graphics, we talked about the sRGP and fix. Yes, they were also had some of these features. There were some device dependent graphical libraries coming out by brought out by various vendors, starting from HP to even CERN in the earlier days, but the problem we had was when the graphics program is done by coded by a programmer and you wanted to port it to another system which does not have those support of the libraries, you could not easily make those programs run on any other system. That problem is completely, almost completely removed by OpenGL, and that is why people are quite happy with this particular standards. So, now the next question comes is, what are the features about OpenGL? Okay, what OpenGL does and how it helps you. We will look at some of these features first about OpenGL, and then see what you could do with this OpenGL, and of course, towards the end of the class, if not today in the next class, we will see what you cannot do also. I must admit here, and I must inform you also, that although this is a lecture on software specific standards for graphics, and it will give you only glimpses and highlights of what OpenGL is about and what it is possible for you to do. We will also see some examples in the next class with OpenGL code on a platform. Probably I will pick up Windows platform to show you demonstrations of OpenGL code, but I would request you that when you have a system working, you please download the OpenGL drivers. They are available. Go to the vendor specific website or go to the standard opengl.org site. I will give you those links at the end of the class, next class, if not today, and you should be able to download those device drivers, DLLs, header files, and run your OpenGL. Please run and practice. Pick up a reference manual, pick up a programmer's guide of OpenGL, take some sample codes, get experience, and then try even complex programs, so that you gain confidence. Remember, just listening to these lectures, looking to these slides, looking to these demos does not help you to learn. It will probably trigger off an interest within you. It might just give you glimpses of how to start with OpenGL. You must pick up a programmer's reference manual yourself. Make your system OpenGL ready. Make your system OpenGL ready, and I am sure you will be able to enjoy the features of OpenGL, which are available worldwide for any programmers. Okay, so let us look back into the features in OpenGL before we start to discuss about what is OpenGL. It provides facilities such as 3D transformations, which includes rotation, scaling, translation, and perspective. It provides color models. You have to specify values of a color such as the red, green, blue, RGB, and the alpha. We will describe this alpha factor, but before that we will go to certain features. And also we would like to I would probably like to bring in here what is OpenGL in terms of trying to help you in drawing a picture. Well, the main purpose of OpenGL here is to provide you an interface such that which helps you to render, draw of course, and then render both 2D and 3D objects as well as pixels in terms of bitmap images into a frame buffer. Ultimately, OpenGL addresses a frame buffer. You do not have to worry about the frame buffer address and all that, that is handled by the OpenGL drivers themselves, but it provides you whatever functionalities we have studied so far in computer graphics. If you recollect, starting from transformations to clipping, drawing lines, polygons, circles, ellipses, we looked at good algorithms for VSD rendering, okay, and all those features which we have, all those features are available in OpenGL. But of course, as a computer graphics scientist here and engineer, you must know how those algorithms have been drawn efficiently by OpenGL. That is why we went through all these algorithms as much as possible. But now you do not have to write the Bressenham's code in C or C++. A line draw equivalent command of that is available in OpenGL. In fact, there are much more high level commands to draw curves, polygons, polylines, or even shading. So, the main purpose of OpenGL is to render 2D and 3D objects as well as draw pixels, as well as provide pixels onto the bitmap screen into the frame buffer. And of course, when you talk of rendering 2D and 3D objects, in most cases of course, we will go through a flow chart and talk about the graphics pipeline in OpenGL, all right, but before that I want to give you a picture that you should be able to draw 2D and 3D objects in terms of vertices. So, these vertices are the ones which are the key, which help you to draw lines starting from a single line to multiple lines to polylines to polygons to curves. Most efficient curves will introduce a curve term called nerves, closer to what we understood as B-splines earlier. So, all these are treated as a set of vertices or what are even called as fragments. We will come across this term called fragments, and these are what process to a stage of a OpenGL pipeline. Well, you can visualize OpenGL pipeline similar to the, let us say, the 3D graphics rendering pipeline, which we have studied earlier in our viewing pipeline. Okay, viewing pipeline we have studied. So, you can visualize almost that. We will study this pipeline exclusively, and we will just remember here that OpenGL draws primitives, and when those primitives are drawn, you should be able to operate on primitives. What are those operations? Some of these features are given here. We talk of 3D transformations such as rotation, scaling, translation, perspective, etc. You can put a color. You can put a color onto those primitives. So, OpenGL draws primitives. It draws points, lines, or polygons. Of course, it has several other selectable modes. Okay, you can control a mode which is not given here in terms of color could be visualized as a mode. Color could be visualized as a mode in the sense that when you enter a certain mode, of course, there could be several modes operating in OpenGL, and some of them do not interact with each other in terms of a color may not interact with an animation mode set by you, let us say. Okay, or you could have two different parts having two different colors of a segment. Okay, but in some certain cases the mode do interact depending upon the. So, one must have an idea what mode interacts with the other, what mode does not. You can almost visualize, those with computer science background must, I can speak to them here, you can visualize OpenGL almost as a state machine, okay, where you move on to a certain state and the state remains till you change that state. Now, let us look at a color. If you set a color default to a background, foreground could be red, green, blue, magenta, whatever it is, we talked of these 8 fundamental colors with 3 bits or 256 possible colors with 8 bit and so on. You remember the concept of lookup table, okay, when we discussed about graphics display. So, you can set a particular color, and when you set a particular color and keep drawing primitives such as say points, lines, vertices, polylines. Remember, these are the primitives, very low level primitives. You can of course use an object oriented approach and encapsulate and draw a high level primitives which will take the override on the set of low level primitives provided by OpenGL. That is all possible. But when you are into a mode with a certain color, all those primitives will be drawn with that particular color unless you change that mode. Unless you change that mode and move to another color, let us say in this case I am talking of color as an example of a mode, but it could be something else as well. When you set a particular color, that mode is particular set for all primitives drawn after that till you change the color, then you have basically gone on to different mode. Okay. So, we will look at these features, we will continue with the discussion 3D transformations, color, then lighting. It provides facility for flat shading, Gouraud shading, font shading, etc. And it also provides rendering in terms of texture mapping is a unique feature in OpenGL, where you can map onto a texture onto a particular surface. Okay. And of course, modeling. Here we are talking about primitives to be defined as a group of one or more vertices. Okay. We talked of primitives as points, vertices, lines. You can have primitives as curves. Okay. A vertex could be defined as a point or the end point of a line or a corner or a polygon and things like that. A primitive could be a curve itself. Okay. And when you look at this particular curve, which is called as nerves, is a very new term which I am introducing here with respect to OpenGL. This concept of nerves is available in high level toolkits such as Maya. I gave this example of the software Maya in the introduction of the lecture, which is used for making movies. Okay. Good animation, high quality virtual reality movies are made of Maya, and Maya provides you to create complex objects not only with points, lines, polygons, but it also provides you nerves. Okay. What is nerves? It is a non-uniform rational B-spline. I repeat, remember, you can note down this term, non-uniform rational B-spline. We talked about cubic spline and Bezier curves, a combination of that, where a spline uses the Bernstein basis is called a B-spline. Okay. So, we have these nerves as curves and surfaces, and that is used for defining, that could be also used to define your primitives. Okay. And the data which could consist of vertices, colors, surface normal, texture coordinates, edge flags, which could be associated with either a vertex or a particular curve or a primitive. In its associated data, they are processed independently, and they are processed in the graphics pipeline. The graphics pipeline will process all the attributes necessary for a particular primitive. And the word primitive, I have used it very earlier in the lecture series, and I use it again here in OpenGL. The word primitive does exist, and I repeat, the primitive could be a single point, it could be a single line, it could be a group of lines, it could be a polygon, it could be a shaded polygon or a polyline, it could be a nerve, it could be a simple triangle, it could be a surface. And there are various attributes associated with these primitives. Of course, the first fundamental descriptors which you need for defining a primitives are their x, y, z coordinates, one point or multiple points. Then depending upon the type of a primitive, you could have its surface normal, you could have its color, you could have its texture, you could have other properties, we will see later on, like the material properties of a surface, which could be used for rendering and shading. So, all these are very important properties which are associated with lighting and shading, of which we discussed also in the Phong model and the Gouraud model also. Okay. So, those are important features which must be incorporated as attributes of your primitives. Okay. And there exists an OpenGL graphics pipeline which will process this data. Data means a stream of such requests to process this set of vertices in a certain sequence, not randomly of course, is when a sequence of events starts in OpenGL. Sequence of open events starts, it is an execution model which takes over, okay, and it starts interpreting an OpenGL code, and it could move from one mode to another, and then it starts processing the sequence of the vertices in which the way in which your program is written. Okay. So, we are talking of features of OpenGL which work on a set of primitives in defined by your program, and these are the features. We talked about 3D transformations. If you read to the slide, color models, lighting, you can define more than one light sources, you can have various types of lighting properties, you can define a light based on a certain color, okay, and the surface material also can have a certain color. We talked about this. Okay, where the lighting could be the light color could be different than the surface material color, and of course, they could interact to give you a different phenomena. Okay. The lighting involves various other properties, like it can also talk about the effect of attenuation, atmospheric attenuation, of what is called as the term used in OpenGL called fog, the effect of fog. Okay. We talked of this alpha as a color parameter. If you look back into the slide, in terms of this color parameter RGB, which is traditionally known to you as the 3 components of a color in a cube, we have this parameter called alpha, which is used for blending. It tells you how much transparent an object is. Is it opaque or is it transparent, is it translucent, semi transparent or not. So, OpenGL will tell you or gives you the option of providing whether the surface which you are drawing is completely opaque or not, completely translucent, or it is somewhere in between. So, that is the alpha factor which you provide in a scale from 0 to 1 normalized. Of course, you might have to give a value from 0 to 55 and tell you what is the blending alpha factor for a particular object, surface, or even at a high level I will call any primitive may have its corresponding color, not only in terms of RGB, but also alpha. The color of the light may not have an alpha factor, it will only have an RGB, but the material does may have, or primitives will have an alpha factor. So, coming to the last part of the features in OpenGL, we talked of this atmospheric fog, alpha blending corresponding to this alpha, and you can have effects such as even motion blur. That will be very interesting. It will have concepts such as even motion blur. So, these are the certain features which we had seen in OpenGL, and based on these features we can start to discuss about the OpenGL graphics pipeline. Okay. Let us lead through these features again: 3D transformations, color models, lighting, rendering, modeling, and effects, other miscellaneous effects such as atmospheric fog, alpha blending, and motion blur. Now, OpenGL commands are always processed in which the order in which they are received. Although there may be an indeterminate delay before a command takes effect, this means that each primitive is drawn completely before any subsequent command takes effect. It also means that state querying commands returns data that is consistent with the complete execution of all previously issued OpenGL commands, and the effects of the OpenGL commands will be there on the frame buffer. Okay. And it is ultimately controlled by the window system that allocates the frame buffer resources. The basic OpenGL operations will involve a few stages which we will see later on as we go ahead. Okay. This is the flow chart which will talk of an OpenGL operation, and this is picked up from the reference called the OpenGL reference manual called the Blue Book. Of course, there is a red book associated also, but we can follow one of these for the OpenGL reference. So, as you can see here, there are lots of blocks through which the commands will go through, and finally, it will reach the frame buffer or texture memory. That is the final output which takes place. So, when you are writing an OpenGL command, you are basically issuing a set of, when you are writing an OpenGL program, you are basically writing a set of associated commands, okay, and these commands have to be interpreted. These commands first will be put into a display list. So, what is this command? If you look back, the commands will tell you what is to be drawn and how it is to be drawn. So, commands are you would say I would like to draw a set of polygons. Those polygons could be numbers up to millions, a few millions, a few hundred millions for a more very highly complex picture. And where are those polygons? What are their attributes? How should I lit them up using certain light sources? What should be the atmospheric fog? What is my view angle? You specify all those in your commands, and the OpenGL will take those commands and run it in a particular sequence. Of course, you can have a loop at a certain stage, but still it is more or less sequential. Any of course program in execution works only in a sequential mode, we know that, except when we talk about concepts such as parallel processing and synchronization. We talk of olden days programs from BASIC, Fortran, Pascal, C, they will accept the concept of, let us not discuss bring in the concepts of threads and other parallel processing concepts. It is a sequential program. Okay. Sequential set of commands is what the OpenGL will look at, and it will generate a display list. Okay. So, let us look back. It will generate a display list, and what is that display list? That display list can accumulate some commands for processing at a later stage, at a later time in batch mode, or it can proceed immediately through the pipeline. So, you have these commands ready, and OpenGL will generate the display list. I hope you have not forgotten the concept of display list which we discussed with display devices. Okay. The display list is a sequence of commands which are to be executed. It could be just draw line command, draw point command, draw primitives at some higher levels, okay, but at a lower level it just becomes draw low level primitives of OpenGL. Okay. And that display list is generated by OpenGL from your commands. As you look back, it can accumulate some commands in a display list for processing at a later time in batch mode, or it can proceed immediately through the pipeline. And this is the pipeline. We will see a set of stages of the pipeline. You can see the different stages of the pipeline, starting from evaluator, and per vertex operations and primitive assembly, rasterization, per fragment operations. So, these are the, I can say, the 4 different stages of the pipeline which will generate operations on the frame buffer, or generate a picture on the frame buffer, or generate pixel operations for the texture memory. Okay. So, the next stage, or the first stage in the pipeline which comes, is the evaluator. What does the evaluator do? It provides an efficient means of approximating curve and surface geometry by evaluating polynomial commands of input values. I will repeat, evaluator provides an efficient means for approximating curve and surface geometry by evaluating polynomial commands of input values. The evaluator stage of processing, I must say here, provides an efficient means for approximating curve and surface geometry by evaluating polynomial commands as given here. Okay. During the next stage of per vertex operations, we will see how the evaluator outputs is analyzed. Okay. The per vertex operations and primitive assembly process geometrical primitives. It processes points, line segments and polygons as vertices, and are transformed, lit and clipped to the viewport in the preparation for the next stage. Okay. So, as you see, the evaluator provides an efficient means, it takes the input from the command directly or from the display list, and provide an efficient means for approximating curved segments and surface geometry by evaluating polynomial commands of input values. So, you will have a set of polynomials which are evaluated here, and the per vertex will process geometric primitives. So, at this point we are only processing points, line segments and polygons as vertices, and then they are transformed here if necessary based on the transformation matrix, which we will talk about this. We will open up this block later on, and then they are lit depending upon the light sources. They are clipped if necessary to the viewport in preparation for the next stage. So, as you can see here, these first 2 boxes of the OpenGL pipeline, the evaluator and the per vertex operations and primitive assembly, these 2 together form the different stages of the graphics pipeline, which we have studied earlier in terms of the, when we studied 3D viewing pipeline. If you remember, we had normalizing transformations, clipping, okay, to viewport, and of course, the generated rendering, of course, that comes later on, but when we are talking of those 2 stages mostly, okay, normalizing transformations and then clipping. Okay. So, OpenGL has similar stages in its own pipeline in terms of what we call as evaluators and per vertex operations and primitive assembly. So, if you look back, we are talking about references from the OpenGL Blue Book, where it talks of per vertex operations and primitive assembly. This block processes geometric primitives, point line segments and polygons as vertices, and are transformed, lit and clipped to the viewport in preparation for the next stage. What does rasterization do? It produces a series of frame buffer addresses and associated values using a 2-dimensional description of a point, line segment or polygon. Okay. So, this is a process of visible surface detection and shading which comes here, where this rasterization produces a series of frame buffer addresses and associated values using a 2-dimensional description of a point, line segment or a polygon. Okay. It is important to introduce the concept of a fragment here, which is very, very important. Okay. Now, sometimes although we have seen so far that the OpenGL pipeline is processing the attributes in terms of points, lines, polygons and so on, and it will do all the operations based on those primitives, but there is a concept of fragment here. Okay. And we will see with the output of this rasterization process goes to the fragment, we will see what is this per fragment operation first, and then I will inform you, and then I will discuss what is this fragment concept in OpenGL. So, let us go back. Here we are discussing about rasterization, and the per fragment operation does the concepts of Z buffering and blending of incoming pixel colors with stored colors and masking and other logical operations on pixel values. Well, rasterization we had seen produces a series of frame buffer addresses and its associated values using a 2-dimensional description of a point, line segment and polygon. Okay. each fragment which is produced now, is fed into the last stage, which is called the per fragment operations, which performs the final operations on the data before it is stored as pixels in the frame buffer here. So, these operations include conditional updates to the frame buffer based on incoming and previously stored Z buffer values for Z buffering, blending of incoming pixel colors with stored colors, as well as masking and other logical operations on pixel values. So, the per fragment operations will operate on the frame buffer with the concept of Z buffering, blending with pixel colors or stored colors a priori. It uses the concept of masking and other logical operations on pixel values. When you talk of logical operations on pixel values, it could be a possibility that you can have a different material color and a different light color, and you have to superimpose one on another. And then it is possible that you could like to change either the material color online or the position at the light itself, the light color itself of the light source. And if you do that, you do not want to redraw the entire picture, because in that case not only the redrawing process will be slow, you will be cutting off the scope of animation. So, when you talk of this per fragment operations at the end, which is responsible from taking these rasterization outputs from the primitives being processed in the previous 3 stages of the pipeline, it will load onto the frame buffer. That is the per fragment operations load onto the frame buffer some information about each pixel related with the Z buffering, the color, the masking operations and logical operations with stored colors and also incoming pixel colors. So, it is a combination of these effects at the end, which is latched on to the frame buffer and is handled by these per fragment operations. So, this is what you see as the per fragment operation. What do you mean by these pixel operations now? Okay, we had seen these per fragment operations. Now, the pixel operations mean the input data can be in the form of pixels, that is the image of texture mapping, and is processed for the pixel operation stage. So, this pixel operation also can take input from the display list, okay, or it can set input and output back onto the commands, okay, and it writes onto the texture memory. Okay. So, input data can be in the form of pixels rather than vertices, because it is possible that the commands which generates vertices in the display list can generate outputs to pixels. So, you may have an image data to process. Such data which might describe an image for use in the texture mapping skips the first stage of processing described above. That means, it bypasses all these evaluator, per vertex operations and primitive assembly and rasterization. Directly it goes to pixel operations. So, it skips all the first stage of processing and instead is processed as pixels in the pixel operation stage. So, directly the image is brought here. The result of this stage is either stored as texture memory for use in rasterization process, or even you see a channel link to the process of rasterization itself, or it could be rasterized and then resulting per fragments, the resulting fragments are merged into the frame buffer just as if they were generated from the geometric data. I talked some time back that OpenGL provides you to draw, simulate, basically draw. You could simulate for an engineering application, but it draws 2D and 3D pictures and digital images, that is pixels. These are the 3 primitives. When I talk of primitives or 2D and 3D objects, I will say pixels in the form of digital pixels of a digital image also are a primitive. You can launch that, say I would like to take this input image and do certain manipulations. And it is possible that you could may not have any 2D or 3D objects in your picture. You would like to have a background with a static 2-dimensional frame, a static 2-dimensional background with a digital image of a picture which you like. That could be possible, or you could have a surface on which you would like to map a particular digital image, that is called as a texture mapping. You could have a texture itself or a simple digital image which you could map. So, depending upon that primitive request, which is not a 2D or a 3D vertex, which is a set of pixel, array of pixel values forming a digital image, okay, you would like to process that only, display that only, manipulate that only, or map it onto a surface. So, there are 2 such requests, and based on this, the processing stage in this case will bypass all the evaluated per vertex operations and primitive assembly. It will also bypass at least these 2 stages. It will bypass the evaluator, it does not need the per vertex and primitive assembly operations. you could pass this onto a text memory directly or pass it onto a rasterize operation depending upon what you want. If you want just the picture to be displayed with a little bit of manipulation, you directly pump the pixel operations onto the texture memory. However, if you want this digital image to be mapped onto a surface, then you need to pass it to the rasterization operation and to the per fragment operation. So, as you can see in this picture, from the commands and display list, you have two separate channels coming into the pixel operation stage, and the output could go to rasterization operation or texture memory depending upon the demand, depending upon the task at hand which you want to solve. The output of pixel operations might go to rasterization or texture memory. If it goes to rasterization, it has to pass through the per fragment operations here and then drive it into the frame buffer, okay, because frame buffer typically will have all those vertices based on which you want to map this digital image. Let us say you want to map this or lay over, like you can visualize as if I am laying a cloth on a hilly surface, on a hilly model, on an arbitrary corrugated surface, asbestos sheet you can take, or even a corrugated surface you want to map a particular texture cloth. And you want to do that, that operation can also be done with the help of OpenGL primitives through the rasterization process and per fragment operations in it, because already in the frame buffer you have the per fragment operations is working with those primitives, and you want to put this map instead of putting the color. You want to put this image as a map, lay down the map on this. It is something like take the map and put it on a globe, on a sphere, that becomes your globe. If you take a two-dimensional image of the world map and try to wrap it around a sphere, it becomes a globe. So, that is a simple example of an operation of what I mean by taking a digital image and processing it on a certain primitive. Okay. Here primitive is a sphere, okay, and a two-dimensional digital image of the world map could be your digital image or the pixel which you are operating on. So, the operation requires that you take this map and encapsulate or wrap around this sphere to generate your globe. So, that is a distinct possibility. It is very much possible with the OpenGL, where you use the link to the rasterization operation, per fragment operations and frame buffer, and the input data in the pixel operations, again I repeat, could be in the form of pixels, which is a digital image for texture mapping, and is processed in the pixel operation stage. So, OpenGL operation, when we talked about, we are talking of geometrical data which follows, which in the form of vertices, lines and polygons, which follows the path through the row of boxes which we have shown in the previous slides, that includes evaluators and per vertex operations, while the pixel data, which could be in the form of pixels, images and bitmap, is treated differently for a part of the process, for a certain part of the process that is treated differently. For both types of data, we undergo the rasterization and per fragment operations before the final pixel data is written onto the frame buffer. In the per vertex operation stage of processing, each vertice's spatial coordinates are transformed by the model view matrix. We will come on to this model view matrix later on, which is a part of the evaluator and the per vertex operations, while the normal vector is transformed by that matrix's inverse and renormalized if specified. We will talk about this in detail later on. We will skip this part. The rasterization process produces fragments, not pixels directly, which consist of color, depth and a texture. So, that is a definition of a fragment, which will say that fragments is not pixels, but it consists of a set of pixels with color, depth and a particular texture. And tests and processing, various tests and processing are performed on these fragments before they are written onto the frame buffer as pixel values. So, the per fragment operation will do a lot of processing and tests on these fragments before they are written onto the frame buffer as pixel values. So, this is the description overall of the various stages of the OpenGL pipeline. We start with primitives, again to give a brief summary, and this primitives could be in the form of 2D or 3D vertices or simple digital pixels, and depending upon the requirement, the commands will generate a display list or pixels for the pixel operations, and there could be two different channels for processing, one through the evaluator, per vertex operation, primitive assembly, then through the rasterization and per fragment operation, or the pixel operations could go directly onto texture memory for simple pixel operations, image based manipulation, let us say, okay, which could be set of image processing tasks, okay, which could be view this image with a certain contrast enhancement or remove noise, remove blurring, and those effects, image processing operations could be done on those. Okay. And the other channel could be that these pixel operations are passed through the rasterization process and the per fragment operations to work on the frame buffer directly with and along with this along with these fragments, which consist of information about color, depth and texture information coming out of these pixel operations. Okay, so that is the brief description about OpenGL. I would have loved to spend more time on this OpenGL pipeline, but we have to discuss a few more aspects at least today before we take up OpenGL programming examples in the next class. We talked about abstractions. Let us look at abstractions of OpenGL. Let us look at abstractions of OpenGL. If you look into the slide, the graphical library for OpenGL will consist of primitives, points, lines and polygons. Primitives, points, lines and polygons. It can provide shading and color. It can provide translation, rotation and scaling. It can provide viewing, clipping and texture. It can provide also a hidden surface removal. So, these are some of the features in a graphics library. Okay. It provides you primitives to draw points, lines and polygons, we know that. It can provide concepts of shading and color. It can provide you options of matrix based transformations, 2D and 3D, which we have seen earlier. It can provide view clipping and texture. It can provide hidden surface removal. Okay. So, these are the low level facilities available in OpenGL, minimum any open real libraries. Let us look into the GLU, graphics library utilities. It provides you high level viewing such as perspective and orthographic projection. It provides you image scaling, polygon tessellation. It provides high level structures such as spheres, cylinders and quadratic surfaces. This will be very handy. We have talked about wireframe diagrams, sweep representation to generate certain primitive structures such as spheres, cones, cylinders or even surfaces with the help of curves. Okay. We talked about parametric surfaces and all that. Now, GLU provides you these as direct primitives. It is a big advantage that you do not need to spend time and write your own program, and the program may not need to spend time to generate these. So, you can treat now these spheres, cylinders as an example and quadratic surfaces as primitives, and you do not need to worry about where are those x, y, z, how many precision you need to give. That of course, you have to decide, all right, but you need to come up with a sweep representation to generate your x, y, z vertices for your sphere. So, that is what GLU provides. And at the end, what is a GLUT? I am sorry, the GLUT provides you, it is basically a windowing toolkit for interfaces for keyboard, mouse handler and other Windows events. So, GLUT is basically interface to Windows. Okay. And of course, there are a whole lot of other operations with the GLU and the GL did not provide, it is not in the list here. Okay. You must go to the open reference manual to come up with a list of such flexibilities which are provided. If you look back, I have just talking about translation, shading, color, primitives and all that, and along with the operations to create vertices which may have certain flags, colors, matrix transformations, lighting and color. You can generate textures, you can generate various primitives, various types of clippings are possible. You can provisions are provided, transform to window coordinates, rasterizations, you can generate pixels, generate bitmaps, texture memory, and then of course, you have the concepts of fragments. You have the, we will discuss about the concept of fog, about atmospheric attenuation, about the concept of tests which are done on fragments such as scissor test, alpha test, stencil test, depth buffer test, blending, dithering, logical operations on pixels, copying pixels operations, frame buffer operations on pixels, and so on and so forth. So, these are various types of operations which are possible in the OpenGL and GLU. Now, it is not possible in a short frame of time to discuss each and individual of these commands, because this is not a lecture series only on OpenGL. As a part of to kickstart you on OpenGL, that you get excited and start to use it. Of course, when you see some examples about these programs really working on my system, you will be able to see really get excited and see how it could be worked. So, coming back to abstractions, we have this Windows toolkit of GL, GLU and GLUT. Well, we talked of a 3D viewing pipeline, which is also present in your OpenGL environment, where we have a 3D viewing pipeline which starts with object coordinates transformed by the model view matrix to the world coordinates, okay, and the model view matrix V multiplied by m, which you can set, will transform these object coordinates to world coordinates. Then the projection matrix will transform the world coordinates onto clip coordinates. Then you can have a clipping stage which will take the input of this the clip coordinates and generate what and pass it on to the perspective division matrix, and that will generate the normalized device coordinates. We talked about this canonical view normalized device coordinates earlier, and then of course, we have the viewport matrix which will generate the window coordinates, and output are written onto the device port. So, this flow chart, I must inform you, is taken from the book by F.S. Hill Jr., which is Computer Graphics using OpenGL. Computer Graphics using OpenGL by F.S. Hill. I will give a detailed list of references later on in the next class after I finish the coverage of OpenGL, but this 3D viewing pipeline is different from the OpenGL pipeline which we discussed in terms of the architecture of OpenGL. That was different. This is a 3D viewing pipeline which is similar to the concept of a viewing pipeline which we discussed earlier. We discussed this viewing pipeline. In the class earlier when we discussed 3D transformations and viewing. So, you can see that this 3D viewing pipeline of OpenGL is exactly the same, almost similar to what we discussed earlier. Okay. So, these coordinates which are passed on, if you see here, the object coordinates passed on by the model view matrix generate world coordinates, projection matrix generate clip coordinates after clipping, and perspective division generates the normalized device coordinates, then a viewport matrix will generate the window coordinates which you put onto the viewport. Okay. So, this is the overall viewing pipeline, and just to wind up what we discussed today, we started with why OpenGL, then we discussed the features of OpenGL, we discussed about the various stages of the OpenGL architecture as such, okay, and its features, and finally, the 3D viewing pipeline. Not all the features which we discussed today here, but I just try to give you as much of the list of features at least orally, if not by the full list. We will discuss a few of these when we get into the code of the OpenGL later on in the next class, but remember OpenGL is a state machine, that is what you must also remember, and you can put it into various states. These states may not intermix with each other, but sometimes you must be careful when they are interacting. The color of one of the light might interact with the color of the material. Okay. It might interact with certain animation stages which you are putting through these vertices through. Okay. And you can put it to a static state, into a motion state, both in terms of the drawing pictures and then manipulating these pictures. Okay. And with these words, we would like to wind up the discussion on the first lecture on OpenGL. In the next lecture, we move on to further few more features about OpenGL, and basically the structure will open up with the structure about the GLUT program. Will not be, time is not permitting me to discuss about the structure of OpenGL program right now, but I will discuss that we will follow the GLUT structure program based on C++ syntax. So, please go back and look into C++ features, may not be object orientation to start with, but we will follow the syntax of C++ programs and then move on to certain examples and functions, and I hope you will be delighted to see some OpenGL programs really working on my machine. Thank you very much.